Today we're going to learn about chemical and physical properties of matter. Now, last week we did a reading and we know that matter is anything that has mass and takes up space. All matter, irrespective of its phase or its state, has two types of properties: chemical properties and physical properties. A physical property is a characteristic of a substance that can be observed without changing the substance into another substance. In other words, you can see it without changing what you're looking at into something else. Physical properties can be either extensive or intensive. Extensive properties depend on the amount of substance that you have. Examples include volume, mass, size, and weight. Intensive properties, on the other hand, don't depend on how much you have. Examples would include density, melting point, and boiling point. A good way to think about this is, if we think about water, we know that water boils at 100 degrees Celsius. The boiling point is 100 degrees. But it doesn't matter if I have 10 mils, 100 mils, or 1,000 mils. The boiling point will still be 100 degrees Celsius. So intensive properties do not depend on how much of the substance you have. Extensive properties do. Other examples of physical properties include color, hardness, odor, taste, state of matter, texture, luster, flexibility, heat conductivity, electrical conductivity, solubility, shape, viscosity, ductility, and malleability. All of these physical properties can be measured or observed without changing the substance into something else. I could easily observe the color of a powdery substance without actually having to change it into something else. And that's the key here with physical properties. They can be measured or observed without physically changing the substance into something else. A chemical property is a characteristic of a substance that can only be observed by changing it into a different substance. Examples would include the ability to burn, ability to tarnish, ability to rust, ability to decompose, ability to react with other chemicals, instability, and ability to do acid-base reactions. So now we're going to take a look at the difference between physical and chemical changes. So what is a change? A change is the act of altering a substance. It's an event, something happens. And these changes can be physical or chemical. We're going to take a look first at physical changes. So when a physical change occurs, we do not alter the chemical composition or the identity of the substance. The paper remains paper, or the white talcum powder still remains white talcum powder. No bonds are broken, therefore no new substances are made. These types of changes, physical changes, are easily reversible. So here the diagram just shows this idea in picture format. We have a make-believe substance that happens to be made up of molecules that have a red atom and a blue atom. Over here on the right, after the physical changes occurred, whether that's, ripping the paper in half, the substance, the paper, is still made up of the same type of atoms. We still have the red and the blue, and they are still joined together. So we haven't broken any bonds to create a new substance. It's exactly the same. Examples, like I said, would include when we change something's size, like ripping a piece of paper, melting ice, so an ice cube to liquid water. It is a phase change that is considered a physical change because at the end of the day, the ice cube is water, and then the melted ice cube is still water. freezing Kool-Aid, tearing paper, boiling water, stretching silly putty. These are all examples of physical changes. We're not actually physically changing the material itself. What the material is remains the same after we've done that physical change. Chemical changes. These do alter the chemical composition, and that means the identity of the substance. So we're making a new substance. Bonds are broken and new substances are made. Chemical changes are often called a chemical reaction. Examples would include burning paper, digesting food, rotting, and iron reacting with oxygen gas. If we take a look at the picture, our make-believe substance is made up of those red and blue atoms joined together. But after the chemical change, what we see is we have made a new substance. Now our substance is made up of two blue atoms combined, and then we've got the two reds. So we're making something new, and that's the big takeaway here for chemical changes. We alter the identity of the substance. We turn it into something else. So let's practice. Is it physical or chemical? So are these examples of physical changes or chemical changes? The key here is to think about, are we actually changing the item? When we go through this change, are we changing it from one thing to another? And if the answer is yes, then more than likely it's going to be chemical. So let's think about cheese. When we melt cheese, does it change into something else, or is the cheese still cheese? Melting cheese would be a physical change. Burning wood. Are we making something new? Is that wood being turned into something new as it burns? This one would be chemical because we have the wood burning, and as it does so, we are creating carbon dioxide, and also the wood is being turned into ash and charcoal. So we have new substances being created. Therefore, burning of wood would be considered chemical. Sour milk is chemical. Wadding up paper. Wadding up means to take a piece of paper and like screw it up into a ball. Ultimately, after I do that, the paper's still paper. And then a bicycle rusting, that would be chemical because we're creating something new. When a bicycle rusts, we're creating iron oxide. That's the iron from the bike reacting with the oxygen in the air. The law of conservation of mass. When chemical changes occur, matter is never created nor destroyed in those reactions. What goes in, so the mass of the reactants, what goes in, equals the mass of the products, the thing that comes out. Why is that? Well, we kind of saw the answer in the little diagrams of the molecules made up of the red and blue atoms. During a chemical change, the atoms they don't just disappear, they're still there. They're simply rearranged into new substances. So we do not create nor destroy matter, so none of those atoms and molecules are ever created or destroyed. They're simply broken and re-put back together in different ways to create different products. So parts of a chemical reaction. So during a chemical change, I talked about how reactants, the things that go in the reactants, equals the products. So the mass of the reactants, what goes in, equals the mass of the products, the things that go out. So this is just a review of the key vocabulary. Reactants means the substances that are broken down by the chemical change. It's the things you start with. And then the products, these are the things that are created. These are considered like the output, the things that are created. And then that arrow means yields, means to turn into or to make. So what is some evidence? So when we look at something, can we identify that a chemical reaction has occurred? So evidence for a chemical reaction could include the evolution of light. That means giving off light. We might see changes in temperature, whether it's a positive increase, so the temperature goes up, or do we see the temperature come down? Another piece of evidence to suggest a chemical change has occurred, a chemical reaction has occurred, would be the formation of new gas or bubbles. We might also see a color change. This one is illustrating that the iron has turned into rust, iron oxide, and we can see that in the picture there, that red kind of speckled appearance. And number 5, the formation of a new precipitate. So here they're pouring two liquids together, and what they're doing, or what you see happening, is a precipitate, a solid is forming. So they're creating something new. So evidence of a chemical reaction. This is just showing you how what goes in equals what comes out. So if I start with 226 grams of iron, and that reacts with 93 grams of oxygen, what is created is rust, and we would end up with 319 grams. So we're not creating or destroying matter. It is being conserved, because 226 plus 93 is going to give us our 319. So why do we need to worry about chemical and physical properties? Why do scientists even care? Well, it helps us to make some really important decisions. For example, titanium is a very strong metal, and it doesn't rust, so it is often used in jet engines. Definitely wouldn't be something we would want to use in our car. It's very expensive, but when we need something that's strong and doesn't rust, and the best bet would be to use titanium, certainly acceptable for a jet engine. Titanium is also non-allergenic. That means people don't have allergies to it very often, so it would make, or it does make, a good metal that they use for making artificial joints and earrings, things for piercing. Tungsten is usually used as a filament in light bulbs because it has the highest melting point of any metal. It glows red when hot, when electricity runs through it, and it gives off both heat and light. So really understanding these physical and chemical properties enables scientists to make the best decision about what metal that they should be using in whatever they're working on, or whatever they're trying to make.